Can you hear me?
Yeah.
Good. All right. Guess it's time to start. So today I'm changing topics, and for the rest of these lectures, I'm going to talk about Cerf's theorem that pseudo-isotopy implies isotopy, at least for high-dimensional simply connected manifolds. So let me just set up what all these terms mean. So we've talked before that if you have a submanifold of a manifold, everything here is smooth. An isotopy of X inside M is simply a map of the interval into the smooth embeddings of X into M, a smooth map. Which means that if you look at the map from X cross I into M, this is a C infinity map. And of course, capital Phi, it's an isotopy from little phi if at the origin in the interval you have the original map. Okay, so for example, we imagine you have a knot in the 3 sphere or in 3 space. You move it around, but you don't allow any crossing. It's always embedded. That would be an isotopy of the knot. Now, as we've seen before, there's another convenient way to think about this, which is not to view this as a one-parameter family of embeddings of X into M, but view this as an embedding of X cross I into M cross I. You see, an isotopy doesn't have to be an embedding. It's just at each slice you have an embedding. Forgot to say that. So an isotopy is a smooth map from X cross I to M, whose restriction to each X cross T is an embedding, but overall it can meet itself. Different slices can meet each other. So you can get to a situation where you have an embedding by simply looking at diffeomorphic embeddings of X cross I into M cross I, preserving the I factor. In other words, phi of X comma T is simply let's call it phi hat, what I used to call phi of XT, which was a point in M, comma T. So our picture might be, here's M cross I, and here's our manifold X, and we have some embedding like that, preserving this time slices. Now, a special case of this, an isotopy of the manifold M. So phi, an isotopy of M is an isotopy of the identity of M. So in other words, it's a map from M cross I to M cross I, a diffeomorphism. Phi of M0 is M, so it's the identity at level 0. Phi of MT is some phi sub T of MT, and the whole map is a diffeomorphism. And that's an isotopy of M, by which I mean an isotopy of the identity embedding of M into itself by diffeomorphisms. And one of the results, classical results I've used, is that if you have an isotopy of a submanifold in fact, it's the restriction of an ambient isotopy of the ambient manifold to the submanifold. Every isotopy of X in M is the restriction of an isotopy of M. Okay, so that's what an isotopy is, and we'll denote, well, maybe one more definition, and then I'll introduce some terminology. If F is a diffeomorphism from M to M, we say an isotopy from F to G, another diffeomorphism, is a level preserving diffeomorphism M cross I to M cross I, level preserving. Level simply means the T coordinate, such that phi 0 is F and phi 1 is G. So instead of starting at the identity, an isotopy from F to G starts at F on this end and ends at G on that end. Of course, it's completely clear that F is isotopic to G if and only if, what shall we say, F inverse composed with G is isotopic to the identity. So we'll denote by I of M the space of isotopies of M. And here, when I don't specify what it's an isotopy from, I always mean it starts at the identity. So this is the collection of diffeomorphisms level preserving diffeos with phi 0 equals the identity. And this is a group, infinite dimensional Lie group, under composition. If you have two level preserving diffeomorphisms starting at the identity from M cross I to M cross I, you can compose them to get a third. You can take the inverse diffeomorphism, it's also level preserving and starts at the identity. That's the inverse operation in the group. So isotopies form a group, and this equivalence I was talking about up here is F is isotopic to G if and only if F and G are in the same orbit of an action of the isotopies on the diffeomorphisms. So the isotopy group acts on the diffeomorphisms by composition. If you have a diffeomorphism F, you take F cross the identity on the interval. That's a map from M cross I to M cross I. And then you can compose with an isotopy, get another map from M cross I, and take the restriction at level 1. Okay, then F would be isotopic to G. In other words, you just compose the isotopy with F on the first factor and the identity in the second factor. Okay. Now, there's a closely related notion of pseudo-isotopy, which in the world of embeddings is called concordance. So let me start with that, concordance of knots. So we've decided that an isotopy of knots can be viewed as an embedding of S cross I in S3 cross I. An embedding I preserves the T, so it's level preserving. This is an isotopy. So you have an annulus in, so here's the 3-sphere cross I. Here's your knot, and you have some embedding, which is level preserving embedding. That will be an isotopy of the knot. Concordance of the knot is an embedding of S cross I into S3 cross I that sends the boundary to the boundary. S1 crosses 0 is inside S3 crosses 0, and S1 cross 1 is in S3 cross 1. So we get knots at the end. Again, back to this picture. So here's our knot at level 0, K0. Here's our knot at level 1, K1. And we have an annulus connecting them inside the sphere cross I. Then we have an annulus connecting them. But we do not assume that the annulus, that the map preserves the T coordinate. It preserves 0 and 1, but it does not necessarily have to preserve the intermediate. So the annulus, if I can draw a picture down a dimension, could be embedded like this. So that when you slice by the time directions, you don't get a function without critical points. You introduce critical points where the topology of the cross section changes. That's a concordance. So that's a concordance for knots. Is the same notion of concordance of embeddings in general. If you have the embeddings of X into M, you would say F and G are concordant if there's an embedding of X cross I in M cross I, sending 0 to 0 and 1 to 1. So X cross 0 goes to M cross 0, X cross 1 goes to M cross 1, but otherwise it's just an embedding. So it doesn't preserve the coordinate, T coordinate. Not necessarily preserving T. If it preserves T, then it's an isotopy. Otherwise, it's just a concordance. And there's a natural question. Can you have embeddings that are concordant and not isotopic? And the answer is in general, yes, even for knots. If a knot is concordant, well, I can't really draw a knot here on the spot. If a knot is concordant to the unknot in the sphere, then you could fill in over here a 3-ball and fill in the knot by just adding the central disk. So a knot is concordant to the unknot. So K is concordant to the unknot, let's call it U, if and only if K, which is in S3, bounds an embedded disk D2 in D4. And it turns out that there are lots and lots of knots that bound disks D2 and D4 that don't bound disks in the 3-sphere. And these are called slice knots. I'm not going to give you examples, but there's a huge number of slice knots. So in general, concordance and isotopy are very different notions. Now we can consider the special case for isotopy of manifolds. So we can introduce what's called the space of pseudo-isotopies. It's going to be denoted script P of M, calligraphic P of M. It's simply the diffeomorphisms M cross I into M cross I that send their diffeomorphisms, so they send the ends to the ends. Phi of M0 is M0. So at the 0 end, they start at the identity, and that's it. They don't necessarily preserve the T coordinate, but they do send M cross 1 to M cross 1. So you get a map from M cross I to M cross I, which is the identity here, and it'll give you some diffeomorphism at the other end, F, but it doesn't preserve the T coordinate. In this context, F is said to be, F is pseudo-isotopic. To the identity. And there's a notion of F is pseudo-isotopic to G, which would simply be, you look at diffeomorphisms that are F on one end and G on the other, and this is equivalent to saying F inverse G is pseudo-isotopic to the identity. Okay. And these form a space under the C infinity topology. I've already said what it is. It's the space of pseudo-isotopies. These are also a group. These form a group under composition. This is, of course, another way to form at least a semigroup structure, which is given two isotopies or pseudo-isotopies, stick them end to end and make a longer isotopy or pseudo-isotopy, and then rescale so that the parameter is 0, 1. And by the usual sort of arguments in topology, that gives you the same group structure, but I won't go through that. We're only going to use the composition group structure. So the pseudo-isotopies form a group, the isotopies form a subgroup. They're not the same, of course. And the orbits, so F is pseudo-isotopic to G if and only if F and G are in the same orbit of the action of the space of isotopies on the space of pseudo-isotopies. This is a subgroup, so it acts. Okay. So the question now, equivalent to the concordance question, is, what's the difference between isotopy and pseudo-isotopy? Are they the same? If they differ, how do they differ? And now we come to Cerf's theorem, fundamental theorem of Cerf. In the 70s, let V be a closed, simply connected manifold of dimension at least 5, then a diffeomorphism F from V to V is isotopic to the identity if and only if it is pseudo-isotopic. Unlike the case of knots, where you can have these annuli embedded in S3 cross I that can't be straightened out to be an isotopy, if you have a high dimensional manifold and a diffeomorphism of it, and then some twisted diffeomorphism of M cross I to itself that starts, say, at the identity, you can straighten that out, straighten that diffeomorphism out so that it is not only a pseudo-isotopy, but it becomes an isotopy. So that's Cerf's theorem. Now, the next thing I want to show you is how this is related to Morse theory. My lectures have been about various aspects and applications of Morse theory. So how is this theorem related to Morse theory? Well, so let me talk about, so that's the next thing I want to discuss. How is it related to Morse theory? And then the second topic for today is an overall sketch of the proof with an overview of the proof, sort of outline the nature of the steps, but not try to give any justifications for any of the individual steps in the argument. Okay. Okay, so let's talk about the action, well, maybe the orbits of the isotopy action on the pseudo-isotopies. Okay. So the way to think about a pseudo-isotopy, here's my picture of a pseudo-isotopy. Here's the manifold V, and here's the direction T. I have a diffeomorphism of V cross I. So here are the slices of V cross I, and they go into V cross I, but the image slices will not be the standard. So these are the images of the various slices, V cross T. So a pseudo-isotopy gives you a picture inside V cross I of a bunch of slices. Each one is diffeomorphic to V, and the slices are labeled by their T variables. So each one of these slices has a T associated with it, namely it came from V cross T over here. So you use that T and you have a picture of the slice. So we have some varying family of slices with the notions of T. And now the claim is that two of these, phi and psi, are isotopic. So they're in the same orbit, if and only if these pictures are the same, if and only if the images of the slices phi of V cross T and psi of V cross T are equal, with labels. Well, I guess that's, the label is the T, right? So in other words, you have two families of codimension 1 submanifolds filling up V cross I. Each one of the submanifolds has a label T. The two diffeomorphisms are isotopic if and only if the pictures are the same. The labeled pictures are the same. Okay. Of course, we can't really draw a picture because it's an uncountable number of slices, and the proof is completely trivial. Look at, see if I get the direction correctly. Look at phi inverse psi of V cross I to V cross I. Okay, well, psi of VT, of course, well, so the pictures are the same. That means it's psi of V cross T equals phi of V cross T. That's the statement that the pictures together with the labels are the same. So phi inverse composed psi, phi inverse composed psi of V cross T is V cross T. Just taking, take phi inverse of this equation. So that says if you go in by psi and come out by come back out by phi, you get a level preserving diffeomorphism from V cross I to V cross I. So this is level preserving. And that means it's an isotopy. If we let it act, say, from the right on phi, under composition, we clearly get psi. So this is an isotopy. Acting on phi, you get psi. Okay, composition from the right. So how can these two phi and psi differ? If they have the same picture, the only difference is the way each of these slices is identified with the standard V over here in the domain. Phi and psi will give you different identifications. So the composition of one followed by the inverse of the other, I guess I did psi and then phi inverse at level T is a map from V to V. It's a diffeomorphism. So over here, we have the standard V. We come into this funny slice. We come back out, but that slice goes back to the standard V. But nobody tells me that the map is the identity on the V's. That's the isotopy. It's how these slices are labeled not in the T direction, but in the V direction. You get different labels by phi and psi, and those labels vary smoothly as you move up T. They start at the identity because both phi and psi are the natural identification across here. And that's your isotopy that acts on phi to give psi. Okay. All right. Okay. So how do we get to Morse theory? All right. So first I want to define a map from the space of pseudo-isotopies to a, well, let me back up a second. Let's consider the space, which I'll call f of v. These will be C infinity functions from V cross I to I that send V cross 0 to 0 and v cross 1 to 1. So let me write it this way. So C infinity functions on v cross I into the interval that send the bottom to 0 and the top to 1. Well, this is naturally a subspace of the C infinity functions from v cross I into R, which is a Fréchet space. It's a vector space under addition of functions, scalar multiplication. And this submanifold is given by the equations that F restricted to V cross 1 is 1, and F restricted to V cross 0 is 0. These are affine conditions. Infinite codimension affine conditions. If I had F restricted to V cross 0 is 0 and F restricted to V cross 1 was 1, that would be linear conditions. So I'm just shifting the linear condition by a constant. So I get an affine condition. So the space F of V of these diffeomorphisms sits inside this vector, this Fréchet vector space, as an affinely closed submanifold. Okay. Well, now maybe let's call this F hat because I want to cut down a little bit more. Now I want to take F in V inside F hat in V to be those with the property that those F such that F inverse of 0 equals V cross 0 and F inverse of 1 equals V cross 1. So these are C infinity functions from V cross I to I. They send V cross 0 to 0, they send V cross 1 to 1, and they send V cross the interior of the interval to the interior of the interval. So that's the extra condition. And this is, F is clearly an open convex subset of F hat. These are open conditions, okay? And they're convex. If you have two C infinity functions with this property, and you take the standard interval, if you have F naught and F1 with these properties, you take T F naught plus 1 minus T F1, it also satisfies the property. So this is a convex subset of an affine linear submanifold of a Fréchet vector space. That implies F of V is contractible. I mean, certainly implies the homotopy groups are trivial, but actually it implies that it's contractible. So this is a contractible set of functions. Just connect anything to the identity, well, to the projection by this path, and you get a contraction. Now we're going to be interested in a subspace of functions inside F. These are functions without critical points. The paradigmatic function without critical point is the projection onto the second factor. It certainly satisfies all my conditions. It's a C infinity function. It takes V cross 0 to 0. It takes V cross 1 to 1. It takes V cross the interior of the interval to the interior of the interval. But in fact, what we're talking about in general is maps of V cross I into I, Morse functions sending the endpoints to the endpoints without critical points. Okay. All right. So now I want to define a map from the space of pseudo-isotopies to these functions without critical points. And let me see if I need. Oh, I forgot to give corollaries of the Cerf's theorem. I'll come back to that in just a second. Yeah, so given a pseudo-isotopy, I assign it the following function: projection on the second factor followed by the inverse pseudo-isotopy. So back to my pictures. Here's my isotopy and my pseudo-isotopy. If I take phi inverse, it will carry these varying level sets back to the standard level set, and then I take pi 2. So this is simply the map that associates to the level v cross t, t. In other words, if I call this map f phi from v cross I to I, this is simply the map f phi inverse of t is phi of v cross t. So it's the map of v cross I to the interval whose level sets are these images of the standard level sets under phi and with the same labels. Okay. So if you want to know where a point goes under this composition in the interval, you simply, where the point goes is telling you which t has the property that this twisted level set vt contains the point. All right. So pseudo-isotopy, I should have said this earlier, pseudo-isotopy implies isotopy if and only if the space of pseudo-isotopies is path connected. Okay. So the statement that pseudo-isotopy implies isotopy is equivalent to the statement that the space of pseudo-isotopies is path connected. You can connect through pseudo-isotopies, through a one-parameter family of pseudo-isotopies, any given pseudo-isotopy to the identity. Well, the proof is completely trivial. In this direction, if, well, here, let me just give the argument. I'll say that. So suppose I have a pseudo-isotopy phi mapping v cross I to v in P of v. And I have a one parameter family phi s mapping v cross I into I. S runs from 0 to 1. So in some sense, I'm now talking about a two parameter family of maps of v, but I want to think of them as a one parameter family of maps of v cross I. So this will be the S direction. This is the T, and this dot is a copy of V. And then the map here, these maps are the phi S. So phi of 0 is phi. Phi of 1 is the identity. Okay. Then the map F here So F, what is F? It's phi sub 0 restricted to V cross 1. Let's call that F0. F1, which is phi of 1 restricted to V cross 1. We know what that is. That's the identity on V, because this path of pseudo-isotopies goes from the initial pseudo-isotopy to the identity pseudo-isotopy, so it's the identity at every level, in particular. Well, it's the identity. Okay. On the other hand, if I look at Fs, which is phi s restricted to V cross 1, this is an isotopy from F0 to F1, which is the identity. So if you just restrict to the top, you see an isotopy back to the identity from the thing that was the end of the pseudo-isotopy. So F being pseudo-isotopic to the identity implies F is isotopic to the identity if the space is path connected. And the converse is simply because the space of isotopies is itself connected. Isotopies I of M is connected since it is a based path space. In general, if you have a space of paths all based at some base point, that space of paths is contractible by simply contracting each path back on itself to the trivial path. So I of M inside P of M, this is connected. So if every pseudo-isotopy is connected by a path to an isotopy, then since this is a path connected space, the pseudo-isotopies are path connected. Okay. So what we're trying to show is that the space of pseudo-isotopies is a path connected space. Now I've defined a map from the space of pseudo-isotopies to this space of functions. Okay. I claim that this map is surjective. This was phi goes to f phi, which recall was pi 2 inverse compose phi, function without critical points. The claim is that this map, give it a name, mu, is surjective and the fibers of mu are orbits of the action of the space of isotopies on P. Okay. So if we know that, let me give you a corollary, assuming the claim, and I'll come back to prove the claim. P of V is connected, is path connected. If and only if E of V is path connected. Because I've got a fibration, I have a map, and its fibers are all orbits of I of M. So the fibers are connected. The base is E of V, and the map is onto. So if E of V is connected, Oh, and also I'll prove there's a section. The surjective with fibers or orbits of the action, and there is a section. Okay. So suppose I have two pseudo-isotopies. Here's one and here's one. Project them down, I get 2 points in E of V. If E of V is connected, those 2 points are connected by a path. I can use the section to lift the path. And then these two pseudo-isotopies are connected by a path. These two pseudo-isotopies are in the same fiber, and the fiber is connected, so you connect by a path here. So the fibers are path connected. If the base is path connected, then the whole space is path connected. On the other hand, if the space of pseudo-isotopies is path connected, its image in E of V is path connected, but it's surjective, so its image in E of V is all of E of V. Okay, so now let me go back to this map. So now the proof of the claim. So I have this map from P of V to E of V, which sends a pseudo-isotopy to the composite of F2 composed with the inverse. And I'm calling that F of. Okay. Let's first define a section. Well, let's first see what the fibers look like. So if F of phi is equal to F of psi, that's just a statement that pi 2 composed with psi inverse is pi 2 composed with phi inverse, which this is an argument we've already seen. That's equivalent to pi 2 composed psi inverse composed phi is pi 2. That is to say, psi inverse phi is level preserving, which means it's an isotopy. So we have two elements in the same fiber. They differ by an isotopy. Implies that phi and psi are in the same orbit of under the action of the isotropy group. So the fibers are orbits of the isotropy group action, and hence connected. The other thing we need to see is, what did I say? Surjective, and there is a section. Well, a section implies surjective. So the last thing to see is that there's a section from E of the back to the space of pseudo-isotopies. Okay. That's the next thing to prove. To construct a section, I choose a Riemannian metric. On, well, V cross I, the natural way to do it is choose a metric on V and then take the product of that with the standard metric on the interval, but it doesn't really matter. Okay. And now suppose I have a function f from V cross I to the interval without critical points. Okay. So I begin to get a picture. I have these level sets, which are supposed to be the image under the pseudo-isotopy of the standard levels in V cross I. So I have the levels, and they have labels T. What they don't have is V labels. In other words, the projection to I produces this one parameter family of submanifolds because F has no critical points. Those are labeled by their images. So it looks like the pictures we were talking about before that come from pseudo-isotopies, but I don't have a way yet to give the V coordinates along these level sets. Well, I do have the gradient of F with respect to this metric, and I can make it have norm 1 by simply dividing by the norm of the gradient. This is a legitimate operation because the gradient's never 0 because F is without critical points. So this is chi, a vector field, and notice chi of F is 1 because I've normalized chi so that if you evaluate it on F, you get norm gradient squared over norm gradient squared, you get 1. And so chi, now we integrate chi, like C, B, the map from V cross I to V cross I obtained by integrating chi. Okay, in other words, if you want to know where V cross I goes, you take this standard curve here and you integrate it under chi. You'll again get something at level t, because if this was Vt, because the F increases at rate, well, sorry, F at this point will be t. Okay, so this is the way I define the map phi. I simply take V cross 0 as the initial conditions, and I'll take the identity down there, and then for Vt, I send it to the height t point or the time t point on the integral curve. So phi of Vt is the time t point on CV, the integral curve for chi at time t, chi starting at V, at little v. So if you want to know where Vt goes, you start at V cross 0, you integrate chi up to time t, you get a point, and that's the answer, and the usual argument shows that's a diffeomorphism. And since F increases at rate 1 along these parameterized curves, F of this point is t. So it's clear that F of phi of Vt is t. In other words, F composed phi is pi 2, or F is pi 2 composed phi inverse. So I produce a pseudo-isotopy that hits F. It depends only on this choice of a background metric. Therefore, it varies smoothly with the function F, and which, if you smoothly vary F, you smoothly vary the gradient, so you smoothly vary chi. These integral curves very smoothly, so these diffeomorphisms very smoothly, and that's the section. Of course, I can get lots of other sections simply by taking different metrics. So this integral curve, if you will, I had this family of one parameter submanifolds, which were labeled, and I have a metric, so I simply take the perpendicular with respect to that metric in the positive direction. That's my vector field. Unit vector, positive unit vector, perpendicular to these level sets for F. I integrate that vector field, I get the diffeomorphism phi, which produces F under this left action. Okay. So it's come down to, so theorem, I'm going to do it on the time. Pseudo-isotopy pseudo-isotopy equals isotopy. So F is pseudo-isotopic to the identity if and only if it's isotopic to the identity, if and only if E of V is path connected. Well, E of V is a subset of all these functions with arbitrary critical points. They send V cross I to I, they send V cross 0 to 0, they send V cross 1 to 1, and they send V cross the interior of the interval to the interior of the interval. These are the ones with no critical points. These are more or less arbitrary functions. These are no critical point functions. This is path connected. The question is whether or not this is path connected. So pi naught of FV mod, it's a pi naught, pi 1. Pi 1 of FV comma EV is trivial, has only one element, if and only if pseudo-isotopy is equivalent to isotopy. Okay. Let me stop here and give you something I should have done earlier and forgot to do. Give you some corollaries of the pseudo-isotopy result. Actually, excuse me just a second. There's something I have to do. I'll be back in 1 minute. Don't go away.
Remember how I said I got my weeks mixed up because I took long. Anyway, how are you doing your class? You look very presentable. You look very presentable. You want me to get, I mean, I'm not doing anything else. Me to feed you?
No, Monday. Sorry about that. So corollaries of Cerf's pseudo-isotopy theorem. What do I want to say? Let me find the corollaries. Yes, so here's one corollary. Pi naught of diff dn is trivial for n greater than or equal to 6. Okay, so let me prove that. So every diffeomorphism of the disk is connected by a path of diffeomorphisms, that is an isotopy, to the identity. Okay. And the proof is, if you have any diffeomorphism from the disk to itself, the first thing you can do is you can deform F until it's the identity on a subdisk, say of radius epsilon. let's let this be the unit disk, and let's take this subdisk centered at the origin of radius epsilon. That's a fairly standard argument. I won't go through that. So you have the disk and this map F disk to itself, but in here we have the identity. Well, what's left over is a map of Sn-1 cross I to Sn-1 cross I, a diffeomorphism, which is the identity on Sn-1 cross 0. Well, that's that's a pseudo-isotopy. So F restricted to Sn-1 cross I is a pseudo-isotopy. Well, if we can, the path is the space of pseudo-isotopies is path connected, we deform relative to Sn cross Sn-1 cross 0 through diffeomorphisms to the identity. And thus, extending all those by the identity inside, we get a deformation of the diffeomorphism to the identity. Of course, it doesn't fix the boundary. The map on the boundary can be quite complicated. All right. Now let me make a definition. Gamma n. So this is a smooth, let's consider smooth homotopy in spheres. They make a semigroup under connected oriented homotopy spheres. Make a semigroup smooth oriented. So you choose a fundamental class. Then make a group under connected sum. If you have two homotopy spheres, you connect them together, you get another homotopy sphere. Of course, you need the orientation to do that, okay? And for n greater than or equal to 4, these make a group. This is a commutative semigroup structure, so they make a commutative group. The only issue is whether or not they're inverses, and if you change the orientation of sigma, take its class, you get the inverse in this abelian group to sigma, at least in high dimensions, by the H-cobordism theorem. So we have gamma n is the group of smooth oriented diffeomorphism classes of homotopy SNs under connected sum. Okay. And the theorem is for n greater than or equal to 6, I believe. 6 pi naught of the diffeomorphisms of Sn minus 1 gives this group gamma n. So unlike the disk, where in high dimensions, every diffeomorphism this is isotopic to the identity, for the sphere, it's not true that every diffeomorphism is isotopic to the identity, and that difference exactly accounts for this group of homotopy spheres. And the proof is by the H-cobordism theorem I've talked about this before, any smooth homotopy sphere of dimension, well, at least 5, but here we only need 6, is the union of 2 n disks, dn plus, union over the boundary, dn minus. And so the only invariant, is the gluing diffeomorphism from boundary d plus to boundary d minus. This is a map from Sn minus 1 to itself. Certainly, if you vary this gluing map by an isometry, you don't affect the smooth structure on the manifold, but in fact, you have to divide out. So F gives the trivial element Sn if and only if F extends, say, over one of the others, say over Dn minus. So in other words, the group gamma n is the kernel of pi naught of d diff of dn into pi naught of S, that's the co-kernel, pi naught of Sn minus 1, diff of Sn minus 1. But we've already seen in high dimensions, this is trivial. This group is the identity. So the co-kernel is just pi naught of the diffeomorphisms. So that's what this group of homotopy spheres looks like. It looks like the group of isotopy classes of diffeomorphisms of the n-1 sphere. All right. Well, sorry, I should have said that much earlier. So I interrupted my train here to give you these 2 corollaries. But where we've gotten is we have the space of all these smooth maps of V cross I to I with boundary conditions and so on. Inside it, we have this subspace of functions which have no critical points. And what we need to be able to do is, if this is F and this is E, this would be a bad case. If we have 2 points in E, we know we can connect them in F. We need to be able to deform that to a path in E. So since F is connected, path connected, E is path connected, and F is simply connected, every path, every 2 points in E can be connected by a path in E if and only if pi 1 of F mod E is trivial. So I have to deform this path within points being functions with no critical points to a path of functions with no critical points. So so my problem for pseudo-isotopy has become the following. Pseudo-isotopy implies isotopy or is equivalent to isotopy if and only if given any F naught and F1, or given any path, omega mapping 0, 1 into these functions, this function space, with F of 0 and F of 1 without critical points, that is to say, lying in what I'm calling E of V, there exists a deformation of omega, rel endpoints, to a path omega t without omega t prime without critical points for all t. That will, of course, then imply E of V is connected. And we just showed that implied P of V is connected, which was equivalent to the pseudo-isotopy implies isotopy. Well, we're not quite to Morse theory yet, but we're getting closer. We have two functions without critical points and a path of smooth functions connecting them. These are functions on V cross I. So we have two functions, F0 and F1, from V cross I into V with no critical points. And we have some path, omega of T, let's call it omega of S now. Omega of S, a one parameter family, where omega 0 is F0 and omega 1 is F1. But these have arbitrary critical points. And we need to deform omega S, that path, rel the endpoints, to a path in E. So at this point, we need to understand what f of v looks like. So the space of all functions. This is an infinite dimensional space with a stratification. And we only need to understand the codimension 0 stratum, the codimension 1 stratum, and the codimension 2 strata, because we're only interested in studying paths in the space of functions up to homotopy. So the path itself will meet only the open codimension 0 stuff and the codimension 1 stuff. And then to deform the path, we may have to go across codimension 2. So the codimension 0 subspace of F, these are Morse functions with distinct critical values. So different Morse functions where the different critical points all have different values. The strata of dimension 1, there are two types, Morse functions with a critical value with 2 critical points. So as you move around in the space of Morse functions with distinct critical values, you can move 2 values until they become the same. Two critical points, the values become the same. That's clearly going to be a codimension 1 set. Those are some of the strata, codimension 1. The other strata are bursts. So the critical values are distinct. All the critical points are Morse except non-degenerate, except for 1, which is a birth or a death. And as we've seen, that's also a 1 parameter family. I'll talk next time about all other strata, or the codimension 2 strata. All other strata are codimension greater than or equal to 2. That means if omega S is a path with endpoints in E of V, which is certainly in F0, E of V is a Morse function with no critical points, so it has distinct critical values. Omega deforms by an arbitrarily small deformation to a path only in the top 2 strata and meeting the codimension 1 stratum transverse in a finite set of points. points. All right, so I'll finish with the graphic of these functions, this family of functions. So this is the T in V cross I, and this is the parameter S in the family. So we start with, and I want to map the critical points. We start with no critical points on this edge. We end with no critical points on this edge. So this is omega of 0 without critical points, omega of 1 without critical points. We never allow critical points on the boundary, non-degenerate on the boundary. So we never have any critical points hitting the boundary. But we come along and we don't have any critical points for a while because that's an open condition. And suddenly at some point we'll have a birth. And then maybe we'll have another birth. And then these things can start crossing. And then there'll be some deaths. And we end with nothing. So we get some graph here. It's mostly it's a smooth one manifold in the interior of the square, and the only singular points are these cusps, which are either bursts or deaths, depending on the orientation of the cusp, and these crossing points where two critical points have the same critical value. And each one of these arcs is labeled with an integer, which is the index of the critical point. So this would be I and I plus 1. If these two are going to cancel, this would have to be, again, an I and an I plus 1. I could have another component, which maybe looks like this, J and J plus 1. So I get some family almost everywhere. It's a Morse function. And then there are these finite set of points where it fails to be a Morse function, well, Morse function with distinct critical values, where here it's still a Morse function, but two critical values have aligned. Here it's not a Morse function because it's got this codimension 1 phenomenon, a slightly singular critical point. So that's our graphic. That's what the path gives us. And the idea is to start deforming the path to kill off this graphic. By various moves, we'll move these things so that they start to separate. For example, maybe I could move all of this sheet down, all of this region down so it doesn't intersect the higher one. I organize them by the analog of self-indexing, lowest to highest critical points. Then I start using this trading mechanism to trade critical points in 1 degree for critical points 2 higher. I end up in a situation where my graph only has two critical indices, and they're adjacent. And then I have to do argument that involves some of the K theory of the general linear group, a more complicated version of the K theory of the general linear group. GLQZ to cancel all, once you get 2 layers of critical points, canceling all of those somehow in this whole picture. So it is a 1 parameter family of Morse functions with the singularities that are naturally in codimension 1. That's what we have to deal with. That's why this becomes a problem in Morse theory, 1 parameter Morse theory. And with that, I'll stop. Any questions? If there are no questions, see you on Wednesday. So long.